So here's the way in which it was presented a couple years ago. They talked about a spacecraft in orbit. So they had a picture like this. And they said the spacecraft was like right here. And it had a velocity like this. It was going around in a circular orbit this way. And they did ask several questions about the spacecraft, it being in orbit. Things that we are likely to face, like what is the force that causes centripetal motion? They want you to describe that force. And we know that that's gravity. So they're going to ask questions like that. They're going to ask questions about the size of that force. And they're likely to ask questions about whether the mass of the satellite has much of a role in the velocity of the object, of which I want you to remember that no, the mass of the satellite doesn't. Just the mass of the thing at the center does. Because we tend to see the mass of the satellite cancel out in questions regarding how fast it's going to be traveling or questions regarding where the orbit is. Now, what they focused on the question wasn't those things. They focused on something that is a little more obscure, the idea that the spacecraft had to transition from one orbit to another. And that's a little bit about what I want to talk about today, because that's actually how you dock with the space station. You don't go right to it. It takes about a day and a half after you get into a low sustained orbit for the spacecraft to change orbits to go to the higher orbit where the space station is. They can't just launch whenever. There's a couple things you have to realize, that the space station's not changing its orbit. It's going around once every so often. You have to sync up with it. So they have to launch in a very narrow window so that they can maneuver and catch up to the space station. So the real questions I want you to be able to ask are these. When you go from a lower orbit to a higher orbit, do you have to go faster or slower? And does it take longer to go around the Earth or less time to go around the Earth? I want you to find a relationship between orbital radius and velocity and orbital radius and time. We've already done this, but we've not talked about it like this. So the first thing we're going to look at is orbital radius versus velocity. That's the first thing I want to talk to you about. And the answer lies right here. We want a relationship that compares the velocity of the spacecraft with the orbital radius. So it's not hard because it is right here in front of us. The only thing we have to do is recognize it doesn't have anything to do with the spacecraft itself. That we're going to get rid of one of these R's. And that tells us that this is the relationship between the orbital radius and the velocity. Now, I don't know if you see a relationship here, but if I were to move things around, this looks to be a bit of an inverse relationship. Do you guys see that okay? And what I mean by an inverse relationship, if R gets bigger, the velocity we need changes by getting a little smaller. You all follow that okay? Now, that has to do with a combination of things. And although it's not clear here what those things are, I need you to know the qualitative things. So I want you to look here first. When R gets bigger, the force of gravity gets smaller. So there is less force causing centripetal acceleration. There's less pulling on it. So when you go to a higher orbit, gravity pulls less on you. Now, just so you know, gravity still pulls a lot. The acceleration of gravity at the space station is about 7.5 meters per second squared. It's not small. People tend to think they're weightless. They are not weightless because they're not experiencing an acceleration. They're weightless because they're not experiencing a normal force. They're experiencing acceleration. That's why they're in orbit. If you don't know that phrase, you will get the problem wrong on our next test. They are not weightless. They're experiencing a normal force. They're just not experiencing a normal force. They have weight. About 90% of their Earth weight, they still have. They appear weightless because they're not experiencing a normal force. They're falling all the time. But talking about orbits, when you go from orbit A to orbit B, the force of gravity is less. So there's less causing you to change your direction. The other part about this is this side. When R gets bigger, it takes less centripetal force to keep you traveling in a circle. But since the force also goes down, you need less velocity. So that poses a complex problem for rockets. They have to get out to this orbit, but also then have to slow down to stay in that orbit. So the complexities of their maneuvers require that they find a way to go out to this orbit by slowing down. So it's not straightforward what they must do. Generally, what they do is they speed up right here, and then when they get closer to their orbit, they turn around and start slowing down to get themselves settled into the correct orbit. That's how you transition from one orbit to a next. You speed up for a little bit, and then you have to slow down to a point where you were slower than before. I don't feign to understand all the things they have to do. It's complex, and I don't study it. So that's the first thing. To go out to a higher orbit, you actually have to be going slower. Now, the next part is for us to compare the the time and the radius. We do so by recognizing that the velocity is equal to 2 pi r over the period. We talked about this a bit yesterday. We're going to complete that by just doing that substitution and making this comparison again today. So pop that in there, 2 pi r over t, but it is squared. So if you remember yesterday, we got something that looks like this. And then I recommend you cross multiply and get this MEGT squared equals 4 pi squared r cubed. Don't really care about this part. Don't care about this part. Those are constants. We care about these two things. It tells me that if I go to a higher orbit, it will take longer to go around the planet. That shouldn't be a surprise, not a shocker. It's got this r cubed and t squared relationship, but that's mathematical. I want you to have qualitative. Higher orbit takes longer to go around. Simple enough. But you need to be able to explain why. And you need to be able to do so in simple terms. So there's 3 things I think you should be able to connect together. If I go to a higher orbit, the force of gravity is less. We already said that. Your speed has to go down. But the circle you have to travel on gets bigger. Those 3 things. The force of gravity goes down, so your speed has to go down. But the circle you travel on gets bigger. So you're going slower, but traveling in a bigger circle. You're going slower, but traveling in a bigger circle. It's going to take longer to go around. There's just nothing you can do about it. So the space station takes about 80 minutes to go around the Earth. Moon takes 28 days. They're both in orbit. It's just that the moon's much further out than the space station. So there's one final thing about orbits that I really have to impress upon you, and that is it really doesn't matter what you put in orbit. And I've tried to say this before. It has nothing to do with the mass of the object in orbit. So whether there's a big thing in orbit or a small thing in orbit, they all travel the same speed. And that actually poses an issue because we're talking about everything going in the same direction. But we have stuff going in all sorts of different directions out there. So the orbit where the space station is, the speed's about 7,000 meters per second. It's very fast. 7,000 meters per second is hard to quantify when it comes to how fast that is, but it's many, many, many times the speed of sound. So to get to that kind of speed takes a lot. All those objects out there, they're all traveling at that speed. And that's why collisions are so terrible in space. And they're constantly moving the space station out of the way of debris. They have to track everything that's about the size of a baseball and bigger, because a baseball will destroy the space station. So frozen astronaut pee, bits of debris from an old rocket, all of that kind of stuff that's traveling around out there, every one of them poses a huge problem for the space station because every one of them is traveling way faster than any bullet fired on the planet. 7,000 meters per second. We don't fire bullets that fast. The fastest bullets, about 1,500 meters per second. So these things are incredibly powerful when it hit each other. There's almost always a new hole developing in the space station, usually because something small about the size of a pebble rips through it. And they've got to find a way to fix it every single time. So it's kind of a dangerous place, but remember, everything at one of these orbits travels at the same speed all the time. It doesn't matter what their mass is. That's about all for orbits. I do have one final thing that I need you guys to be able to do, and you're not going to like it because I don't like it. I think it's a ridiculous activity. But it doesn't matter. This is one of those activities they want you to be able to do. They want you to be able to do ratio questions. And you've probably never heard of a ratio question before, but it's not a science question, but they want you to be able to make a comparison. Let me give you an idea of what it sounds like. On the Earth, the acceleration of gravity is 9.8 meters per second squared. What would be the acceleration of gravity on a planet with twice the mass but 3 times the radius of the Earth? I'll say that all over again, but these are so common on the exam, it hurts my feelings. The acceleration of gravity on the Earth is 9.8 meters per second squared. What would be the acceleration of gravity on a planet that was twice the mass of the Earth, but 3 times the radius? Is this a problem you can do? I just want to know. If you can, I won't teach you how to do it. If you can't, I'll teach you how to do it. So give it 2 minutes, because if you can't come to an answer in 2 minutes, you're taking too long, because this will be multiple choice. 2 minutes. I've never taught this. So if you're looking past your notes, it's not in there. The only thing you need to do this, though, okay, that's been 2 minutes. Raise your hand if you know how to solve a problem like this. Like you have a plan. Okay, I didn't expect it, but I wanted to see if perhaps you guys knew how to do problems like this. These are ratio problems. They're really not science problems, but they use them in math or they use them in physics all the time. I hate them. So I'm going to give you a method to do this, and it's rock solid. It works every time. I'll give you 2 different methods. You pick the one that you like the most, okay? And then we're going to be done with this. First, you have to get at the root of what they're asking. We were asking about the acceleration of gravity. This is the force of gravity. If I want the acceleration of gravity, I set that equal to ma. That makes it the acceleration of gravity. So step 1, you need a formula. A formula for whatever it is they're looking for. They were looking for the acceleration of gravity. So to get the formula for the acceleration of gravity, I set the force of gravity equal to ma, recognizing that this is one of the objects. So if it's the Earth and me, then this mass is the mass of me. That means that the acceleration of gravity is the mass of the Earth, g over r squared. Now I've got step 1. I have my formula. Now on the Earth, step 2, put in what we know. You don't need the mass of the Earth or the radius of the Earth for this. I know you think you do, but you don't. You need just the result, that the acceleration of gravity on the Earth is 9.8. That's it. That's all you need for this part. The third part is put in what changed. We were told that 2 things changed. We doubled the mass of the Earth, and we tripled the radius. So I put in what changed. I did 2 times the mass of the Earth and 3 times the radius. Now, this part's hard for students, but still work it out. Pull out all the variables. Isolate the variables away from this, meaning I'm going to have a 2 and a 3 squared, but next to that I'll have me g over r squared. I'm pulling away the variables and putting the numbers together. So this is step 4. Isolate the variables. This should be the same formula as before. Should be. This is a multiple now. That tells you how much the acceleration changed. So all you got to do is replace the formula with the value. This needs to be like a 1-minute question when you get it. So I take 9.8, I multiply by 2 ninths. That's a method. If that method works for you, then I don't have to do anything else. If that method doesn't work for you, I have another method. So what do you think? Is this good enough? You want to try a practice one? Okay, here's a practice one. You stand on a moon whose mass is half of the Earth, but the radius is twice that of the Earth. What's the acceleration of gravity on that moon? You stand on a moon whose mass is half of the Earth, but whose radius is twice that of the Earth. What's the acceleration of gravity on that moon? Should be 1.225. Do you want me to go over it? So our original formula is still going to be this one, because we're talking about the acceleration. We had half of the mass of the Earth and 2 times the radius. When I pull out the variables, I get 1/2 on top and 4r squared on the bottom. This is 1/8. And that gives me 1.225. Is that okay? These ratio problems show up on the exam. I hate them, but I don't want you not to be able to do them. I will have 2 on your next test, and they're going to be like this. But remember, they don't have to be about this. Ratio problems can be about anything. You just have to have a formula from which to work. So another practice like this, or are we done with this? Be honest, it's your test. I don't care. Yes, ma'am? Sure. Ready? This is one where you'll need a different formula. Or how about this? One that's just enough different to be harder, but let's see if you can do it. The force of gravity between 2 objects is 10 newtons. You double the mass of both objects, but put them half as far apart. What is the new force of gravity between them? And like I said, I don't like these questions. They don't have much to do with nature, but here we are. You got it? What's that? You hope? I hope so too. Rachel, you got it? Maybe. We gotta work on our confidence. What'd you get? What'd you get?
Oh, it's really, I mean, I got 16. I did the last part wrong.
All right. Caitlin, what'd you get? You get it yet, Noah? Perhaps. What'd you get? Okay. Trevor, what'd you get?
160.
Eisen, what'd you get?
I didn't got an answer, Mr. Shelton.
Okay. So
I got 9.8, but I think it's wrong.
let's see what we get. First, we need to figure out what was being asked. It's two objects, and we're talking about the force of gravity between them. So it's similar to the same equation. We're just using the force equation, not acceleration, the force equation, because I gave the value in newtons. And this equaled 10 newtons. So what did we do to each mass and the separation distance? Well, each mass was doubled. So I take each mass and double it. And then the separation distance was cut in half. So I took the formula. I made the change to each of the variables that was changed. And now I'm going to factor out the variable parts. So I'll have 2 times 2 times m1, m2g. That's on top. And I'll have 1/2 squared times r squared. Just throw that anywhere. It'll be okay. TI? Yeah, they're indestructible. Unless it's a new one. Is it the new one, like with the color screen and all pretty?
No.
Good. Stick with the old ones, man. I've run over them with a car before. It wasn't intentional. In the old days, I used to do this lab where we'd go outside and push the school van. They won't let me do it anymore, but it's kind of fun to like do an accelerator. We'd have everybody get in a van and see how hard it was to push, and then everybody get out of the van and see how hard it was to push, and broke the class up into 2 teams and see who could push it the fastest, you know, somewhere down the street. It was fun in the old days, but they don't let us do this anymore. But one kid dropped his calculator and we ran right over it. He shouldn't have had his calculator out there anyways, but still, that sucker, it lasted. I think I still have it. He gave it to me like as a trophy because he used it on every test from that point forward and still worked just fine. TIs, man, they're indestructible. 2 times 2 on the top is 4, divided by 1/4. And I have the original here, which is still 10. So yeah, 160. 4 times 4 gives you 16. So I will make some of these, but if you can't do them, look, it comes down to like the multiple choice sometimes. The multiple choice problems have to be able to be done in about 1 minute to 2 minutes. So you need tricks to do stuff like this. That's why these kinds of problems are given on the multiple choice. I don't think this problem tells us whether you know anything about the force of gravity or not. But they ask these kinds of questions because they can be done in about 1 minute to 2 minutes. And they are wanting to know if you understand how variables are related. That doubling the bottom makes the force smaller. Making the distance smaller on the bottom makes the force bigger. They want you to understand that. They can do that in a quantitative way here. And that's why they do it. And that's why these questions show up on the exam. Do they have much to do with science? No. You're never going to worry about the force of gravity between 2 random objects sitting on your desk. So that doesn't show up. That's not that important. But they can make a multiple choice question out of it. So you see, that's what they're getting at. Something that they can kind of strike at with you with relative ease. So I'm not going to practice that anymore because we could do 100 of them. And the people who get it, and the people who don't, they'll get better at it a little at a time. I'll make some practice. I'll put it up on Canvas. You practice those kinds of problems if you're having issues. But it's going to be a formula that's on your equation sheet. They're not going to come up with something weird. And the reason they use this one is because there's lots of things they can change, right? They have 3 different variables they can change. Every other equation's only had like 1 or 2 things. That's why they use this one, because it's the first time you've got one with like a square in it, and they're not going to use motion equations. They never do. They always use this one. So we are actually going to transition to another topic for the next 2 days called work and energy. We're going to be doing qualitative, kind of straightforward information about this. Today, I want to talk just about definitions about what these things are. And then Thursday, we'll get into more of the stuff about it. But today, work and energy. And we are leaving dynamics and gravity and all of that and going into a new area of study. And it's kind of nice because although it still uses the concept of force, the best part about work and energy is both of them are scalars. No more vector diagrams. Free body diagrams are going to be a lot less useful. We're going to focus on what the forces are capable of doing and less about what the forces are actually, causing. So that doesn't sounds like I said the same thing, but trust me, it's not. I want to first help you with the definition, and we're going to talk about what the definition of work is. Work is a technical term in physics. It's not your definition of work. It has a technical meaning, and it's very, very specific. So when we talk about work in this class, I am bringing up something that has a specific definition. You're going to have to get rid of your definition. So here's the definition of work. Work is any time a force is used to change something's energy. Work is done whenever a force is used to change something's energy. If this were my mechanics class, I would say that work is the method by which energy is changed. I like to use that phrasing in mechanics because the word method means it's the approach, it's how it's done. This is something that's true in all forms of science, not just physics. That if you want to change something's energy, you must do work on the system. That's the way the word is used. So we say you do work that changes the energy of a system. So work is a method. That method comes down to just three things. In order to change something's energy, you have to apply a force to it. And because of that force, the object has to change position. You have to apply a force, has to be applied to an object, and that object has to change position. That's how you do work. Positive work increases an object's energy. Negative work decreases an object's energy. Again, whenever you use a force to change something's position, you're doing work. Positive work increases an object's energy. Negative work decreases an object's energy. But this is critical. Newton's third law says that for every force, there's an equal and opposite force, which means whenever you are giving something energy, you are taking it away from something else. That has to be true. Now, there's more technically to it, but it comes down to three things. The size of the force, how far the object moves, and this part's kind of weird, but it won't be after a while. It's about the amount of force in the direction of motion. That's why there's a cosine there. If I look at this force, only part of it was used to move the object. The part that was this way moved the object. So only it is part of the calculation. The part of the force that pulled upwards, didn't move the object. That's why there's a cosine here. So you guys who have the FSA tomorrow, good luck. Although I'll see you in the morning, do well in the FSA. And those of you who have to come to class both days, I'll make sure that you get information both days that's useful. So bye, everybody. Have a nice day.
Thank you.